Okay, welcome to the class, folks. So last class we talked about electromagnetic wave. Of course, we also talked about sound wave, and then we learned that sound wave is longitudinal wave, but electromagnetic wave, they are transverse wave, like a water wave, right? So when there is some sort of oscillation, what happens? It generates a wave. So electromagnetic wave is generated by oscillation of electrons, and that generates electric field and then magnetic field, and they can just coexist by generating each other, right? So, and that propagates. That's what we learn. So we talked about, okay, electromagnetic wave is a wave, of course, and light is just a small portion of electromagnetic wave when we talk in terms of, how the wavelength of, let's say, electromagnetic wave from radio waves to the gamma rays. If we look at that range of the wavelength, the visible light is only a very small fraction. That's what we learned. So today, what we're going to do is we're going to build a technique where we draw a ray to represent the uh, light, propagation of light, and then I'm gonna use that to learn about how light behaves with meter, lenses, and so on. And after we finish that, what we're gonna do is we're gonna come back and talk more about wave nature of the light. So for this week, we're gonna be using light rays to describe some of the function or working of the some of the optical instruments. So here in this video you see we can generate water wave by making this thing oscillate. So we can model that as a wave, and the process is similar for the electromagnetic wave as well. There is something oscillating, for example charge, but there is for that wave, electromagnetic wave, we don't need medium anymore. It can just propagate in a vacuum as well. So basically we are transferring energy, and the energy is spreading all over, right? So when we turn on a light, what happens? The energy is spread all over, right? Room gets filled with the light. So we can represent that in 2 dimensions by drawing circles, but in 3 dimensions, it's going to be spheres, right? So if we look at the direction of propagation of the wave, what's happening is this over here, these waves on the water, they are moving something like that. So by doing that, they are just transferring energy. So we can say, okay, the energy is being transferred something like this. And we can say, okay, this perpendicular direction at which the energy transfer takes place, and that perpendicular direction is perpendicular to the wave. We also call these wave fronts. Okay, this is one wave front, this is another wave front, and separation distance between these wave fronts, and that is basically wavelength in this kind of representation. Over here in the water you see one peak here, another peak over there, so distance between two peaks or the crest, and that is called wavelength, right? So we can just measure that distance, and that's going to be wavelength. So in this representation here, this is going to be wavelength. We're not going to be using much wavelength for, a ray model. Okay. So what happens is once it travels farther, as you go, here it looks more curved. It's not that much curved anymore. It almost looks like a straight line if you look at just the small portion here. So same thing goes with the light wave as well. So what happens? They become, like a straight line. But in 3 dimension, what happens? Rather than a line, it's going to be a plane. Okay. And then rays of light, they are perpendicular to those planes. Okay. and rays become parallel to each other. So when source is there, and if you are looking at there, what happens? Those ray appears to be parallel. So over here, when it is closer, they are not parallel. But once we move a little further, what happens? This line segment becomes like a straight line here, a straight line here, and these two like a, you know, let's say a parallel line. So if I were to draw more rays of light over there in that section, what happens? It looks like a straight line. So they become parallel, because another way to look at that is these planes, they are parallel. And since these rays are always perpendicular to these, that means they also become parallel to each other. So if light is coming from distant source, then we say, okay, all these rays are arriving parallel to each other. So to represent the ray model for a light coming from distant object, what do? We draw parallel lines. So, and that's what we do. Okay. So these basically what happens is when the light is coming out, for example, let's say if it is not passing through a very small aperture or hole, uh, then what happens is the light ray model works just fine. Okay, but if we are looking at light passing through very small openings, in that kind of situation, we have to go back and look at the wave, you know, let's say describe in terms of wave property of light, which we're going to be doing after we're done with the ray properties. Okay, so this is basically simplified version. Okay, and we can learn a lot from this. Okay. And then these rays of light travels in a straight line in a medium, but when they go from one medium to another medium, and they get refracted, we say they bent, so we say that's a refraction. And some of them may be reflected, and how much it reflects depends on the nature of the surface at which they are entering or trying to enter, right? uh, and these rays of light, they get absorbed in a medium. For example, right now I have this light bulb on, so the room is filled with light. But what's happening if I turn off the light source? What happens? The light is not there anymore, so they are constantly being absorbed by the source as well. Okay, so now let's look at what happens to the light when it enters, light ray when it enters to the inner face. So here is inner face, and I'm representing this and that, these two, material. So this N represents the property of a material. We call that refractive index, and that is defined as its speed. It means light speed in vacuum versus light speed in some medium. So what happens is light slows down when it goes to denser medium. For example, when light enters from air to water or glass, what happens? When it enters, rather than entering straight, it bends and bends towards the normal. So when it enters the material with larger density. So we don't use density to represent, how much it bends. So rather what we do is we define a property called refractive index of a material. Okay. So for example, if this is water where the light is entering, and then this is refractive index of water. So that means, how do we find that? We divide the speed of light at vacuum, which is constant electromagnetic wave. We learned that 3 times 10 to the power 8 meters per second, right? With whatever speed it is here. And that gives us the refractive index of this material. So that's the best definition. But to find that out, what we can do is, we can measure how much it's bending, and from there we can do some calculation. So this is, let's say, air. So that means refractive index of air is very close to the vacuum. Okay. So for example, refractive index of vacuum is 1. Why? Because speed of light at vacuum divided by speed of light at vacuum gonna be 1, of course. For the light, the speed is still very close to c, but slightly less. So because of that, refractive index for the air is 1.0023, something like that. So if we are just talking in terms of 1, 2, 3 significant figure up to that significant figure, what happens? It is basically 1. Okay, so we can treat that as a vacuum for up to 3 significant figures. So that's what we're going to be doing. So whenever you see it's air, refractive index of air, we're going to write 1. Okay. So now at this interface, what happens? It gets reflected and it passes through, and we call this refraction of light, and we call this reflection of light. So you see here I am showing you angle for the reflection. Both of these angles are equal. But keep in mind that those angles are measured from the normal to the surface. So here the inner face looks like this. So the 90-degree line drawn at 90-degree with respect to that is the normal. So this is called normal. Okay. And this is called incident ray. And this is called incident angle or angle of incident. And this is called reflected ray, and this is called angle of reflection. So if we do experiment and measure the angle, what we find is both of those angles are equal. So that's why I'm writing both of them as a theta 1, or could be just theta. Okay, both of them are same. So sometimes you may see they are written as a theta incident, theta reflection, and that's fine too. Okay, but this, if we write this as a theta reflection, this could be theta refraction, and the notation looks same. Okay, so I try to avoid that. So that is the what we call law of reflection. And another thing about this reflection is that this light that's reflecting and the light that's coming, or incidence, and the normal, they all lie on the same plane. Okay, so what does that mean? So for example, light is coming something like this. And let's see if I have another pencil here. And this is reflected light, okay? And let's say when I say plane, let's think about this, my hand, the palm, as a plane, right? So what happens is the normal we're going to draw on the same plane here on this, on my hand. So the light that is reflected also lies on the same plane. It's not like going away from the plane like that. Okay, so it doesn't go like that. So both of these and the normal, they are on the same plane. So that means if we are drawing them on a paper, it works just fine because paper acts as a one plane. But if the reflected light was sticking out in another direction, a different plane, then showing that something like this would be a little bit difficult. Okay, so that is the reflection. And refraction is given by law of refraction, like what is the angle over here. Let's see if I want to find with what angle it's going to bend, if we know what is angle of incidence. So in this case, theta going to be angle of refraction, not reflection. So this is angle of reflection, this is refraction. Right? So now if we want to know the relationship between these, this relationship is not as simple as this in the case of reflection. Rather, it's given by this equation, also known as Snell's law. Okay. So over here, what you want to keep in mind is that the way this equation works is that the refractive index on the side of the angle of incidence, for example, n1, and then sine theta 1. So that's how it goes. And n2 is on this side, and theta 2 is on that side as well. So we need to keep that in mind. We do not want to mess with that. So in short, this can also be written as a n sine theta is equal to constant. Okay, so we can do that. So when we do that, it becomes more obvious that n and theta has to be on the same side or on the same medium. Okay, so that's all we need to keep in mind. So now here is a question for you, and looks like I haven't started. I thought I did, but here is that. So normal, incident ray, reflected ray, and one of the angle is shown. Okay, and you are asked, okay, what's the value of angle of incidence is, right? So that means it's asking for this angle here. Oops. So I'm going to open the poll, and you have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got. So mostly B, that is correct answer. So we know normal makes 90 degree. So if this is 40, this must be 50. And if this is 50, that also must be 50 because those angles are equal. Okay. So, okay, that's great. So now I have another question for you. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. And let's see what we got here. So mostly C. Oh yeah, a straight line. Turns out correct answer is D, not C. Oops. What happened here? Straight line should be the, shortest time, right? But it turns out that that's not the case because walking on the parking lot is easier walking on the sand, compared to walking on the sand. So what we want to do is that we want to walk a little bit more on the parking lot because walking there is faster compared to sand. So over here we are walking, large distance on the sand, here, here, here. Over here we are walking least, so shouldn't it be E? But what happens is this path. So we are spending too much time here on the parking lot. So it's not that ideal as well. Okay. So it turns out that this path is the, that takes the least time. And that's what the light does. Okay. So for example, when it hits a surface like this at an angle, rather than passing straight, what it does is, let's say if I were to draw a normal here, see this is going to be that angle and this angle is smaller, right? So theta 2 is smaller than theta 1. And it follows this rule. So how much it's going to bend on the inner face, provided this angle depends on the refractive indices. So refractive indices is like, if it is small refractive index, so it's like walking on the park or on the, let's say, parking lot, right? Or paved street. But if light is entering to the water, it's like for it's like a walking on the sand, something like that. It has to slow down. Okay, so that's how it works. And light knows which one the quickest one, and it basically follows that path. So it takes all the path. It tries to take all the path, but mostly what happens is it uses this one that takes the least time. So there is a channel, I think, called Veritasium or something like that. Okay. Recently, I saw a video made by this person. Okay. It talks about minimizing the, like, let's say, optimizing the path. Okay. You may not understand all of those, but kind of that video is somewhat related to this idea as well. So if you are interested, I think this is channel's name. Okay. And so if you are interested and you have time, you can watch that. Okay. So now let's take a look at problem. How do we solve problem using that Snell's law? So in this case, there is this laser beam enters a glass slab. Laser beam is entering from air, right? It doesn't say otherwise, so must be signing from just the air, right? Making an angle 32 degree with the glass surface, it says. So here, this is glass is here, its refractive index is Ng, and refractive index of air, let's say, is Na, which is 1, we talked about. Or if you like, you can say N1 and N2 over here, right? So it's up to you. So now here, let's see, what is incident angle in this case? Let's say theta on the air side, right? With what angle it is entering to the glass, right? So in that formula, remember we have N1 sine theta 1, N2 sine theta 2. So for N1 in this case, it is air, right? And then sine. Do we know about theta 1, right? What is that angle? So can you help me by typing the number on the chat, please? What is that angle? Okay, no numbers yet. So what should be the angle here? For example, this angle for this problem. Okay, so I see there is 32. Okay, okay, keep coming more, please. So that angle is 32, it says, with the glass surface, right? Making an angle with the glass surface. So we don't know how to figure that out. Okay, I see a couple of them, 58. So angle of incidence that goes here is angle made by this ray of light with the normal, not any other angle. So we need that. So our theta A would be that. And because of that, it is 58 degree. Yes. So it's easy to get confused sometimes if we don't pay close attention and remember that these angles are with respect to the normal, not with respect to the surface. Okay. So to remind you folks that I brought this question here. Okay. So what is the beam's direction on the side of the glass? So that means theta g is what? And it says with respect to normal. So it is asking for theta g. If it had asked for angle with respect to this angle over here in this diagram, then you would first find theta g. Oh, I think we are talking about refraction, so should be this. If this angle was given, then what would you, I mean, if this angle was asked, what would you do is first find this angle using this formula, because in this formula, this angle means this one made with the normal, okay? And then from there, you subtract that from 90 and you get that. But in this case, you are asked to find this angle. So that means it's asking for theta g, which goes in the formula, okay? So now ng is 1.5 and Na is 1. So yes, even if it's not given, you can use it as a 1. So now what happens is that using Snell's law, we can calculate that angle. So how do I write that formula? So refractive index on that side is Na. So Na is on air side. So the angle on the air side is theta A. So that's how I need to write it. Okay. So yes, you can write N1 theta 1 sine theta 1. But just to remind you how it works, even with a different subscript, I am writing something like this. So Ng sine theta g. So we are looking for theta g, right? We are looking for theta g, so that means we are solving for that. So we want to move this one to this side. And Na, when we have a number 1 or 0, I like to plug in them, okay? I wouldn't plug in other numbers, but that one, I like it plugging in. So this is going to be 1, means we have sine theta g is equal to sine theta a divided by n g. Okay, so now sine theta a, we figure that out, which is, no, theta a, we figure that out. So we need to figure out sine theta a. and divide that by refractive index of glass 1.5. Okay. So once you have that, theta g, so you need to take arc or inverse. Okay. So in your calculator, it may be written as an arc sine or maybe sine inverse like that. Okay. So you can do that. So this thing goes here and plug that in calculator, and that should give you theta g. Okay. This or that, depending on how your calculator does it. And I have done one such problem in the note as well. So take a look. Hopefully I paid attention which angle was given. I was in rush this time preparing the note. So now let's talk about reflection. So this chapter going to be all reflection from now. We introduced refraction, but we're going to come back to next class and talk about refraction on lenses. Today we're going to talk about mirrors. And this order I'm presenting is slightly different from how it is in the book. Okay. I thought this makes more sense. Okay. So we just talk about reflection first, and then we're going to talk about refraction rather than going back and forth. So that's what I'm doing. Hopefully it does not confuse you. Okay. So how do we see an object? So we have to have some sort of light source. For example, daylight comes from the sun. So those sun rays hit the object, and the reflected rays from the object, they arrive to our eyes, and our eye makes image just like a camera does in our, not on the back of head, but back of the uh, eyeball, called the place called retina. Okay. And that's how we see the object. Okay. So this is the process of seeing object. And when we are standing in front of mirror, what happens? We are getting light from, let's say, our light artificial sources, a light bulb, and so on, right? And then now what happens? You can see the image. So if you look at here, this ear over here is right ear of this baby, right? So this is right ear. So if we look at the image has left ear, which is basically covered here. On the side is left ear. Maybe I should have talked about hand. So this is right hand. Hands are visible here. So this is left hand of the image. Okay. So there is what we call lateral inversion. Okay. So that's what this does. And why does a mirror does the lateral reflection? I mean inversion. So it still makes upright image. That's great. Okay. So we can describe the image making process something like this. Okay. So what do we see is light from an object at some point on the object in this case, right? So this whole thing, so every point, these light are going something like this from each and every point of the object. So if we were to draw all of them, it's going to be mess. So what we do is we just pick a point, okay? And then draw, and we say, okay, that is object. And then we draw, 2 to 3 lines, 2 to 3 light rays. So in this case, I'm drawing one that is going perpendicular to the mirror, okay? So that means it's making 0 degree to the normal, okay? So this is there, this is normal. Maybe I should draw this way. So this is normal. So if light is going something like that, that means it's making 0 degree. So when angle of incidence is 0, angle of reflection also going to be 0. So that means when it goes like that, it comes back retracing that. So that's what you see here. So the black line is going this way, and then blue line is reflected ray of light. So when it hits mirror at normal or 90-degree with the mirror over there, or 0-degree angle of incidence, so in that case, what happens? It just traces back. At all other points, it follows the law of reflection. Okay, so if I were to draw a normal like that, so this angle has to be same as this angle. This angle has to be same as that angle. Okay, so now what happens is these reflected light do not come here and meet with each other. So it's coming from this point, but they are diverging rather than converging. Okay, so what happens is these ray of light don't meet on this side. But when we look from this side, right? So what we see is these rays of light. So our brain thinks, okay, these rays of light are coming from this point over there. And how do I figure that out? I back produce them. Okay. So this is a straight line. So you can put a scale and then keep drawing that line, making it longer, and do the same with the others, right? So when you do that, wherever they meet, for our eyes, for our brain, it appears square. So that's why our eye sees the image of this object over there. But this image is formed not by actually meeting the light, okay? So that's why this image is called virtual image, where the light rays are not meeting, virtual, okay? So this is virtual image. And for plane mirror, what happens? This distance of image from the mirror, we call that image distance, and we may denote that by Q, that is equal to this object distance. So that's why if the baby starts moving away from this mirror, then image of the baby also going to turn around and going to move farther. When you approach to the mirror, your image is also approaching to the mirror at the same rate because of this property. Object distance is equal to the image distance. Okay, so this is plane mirror, but there are spherical mirror as well. So what are those spherical mirrors? It's like we have a sphere. Think about a sphere, not a circle. Here I'm drawing circle, but imagine that's a sphere, right? Soccer ball. And if you cut a section of that, something like this, right? So when you cut that, something like this piece becomes curved inward, right? So when we have this kind of curved inward mirror, we call that concave mirror, okay? And so in that case, let's say we do that and then we polish that side so that this side becomes very reflective one, right? Shiny surface. Remember how our mirror, they are shiny, right? So they are coated. So if we coat this side, this becomes concave. If we were to coat outer side, for example, then this is convex. So the exterior is convex and interior part is concave. So understanding the meaning of the shape are going to be handy because these concave and convex, they have slightly different property. So this mirror, when we cut this piece, it came from like, let's say this whole sphere. So a sphere has a center like this, and it has a radius r, right? So this is a cutout piece and magnified piece of that thingy here, okay? So that's what I'm drawing here. So in that case, the center is here, and distance of center from the mirror is called radius of curvature. And halfway from center is what we call focal point. So Why this is focal point? Because if a ray of light comes parallel to this line, what we call principal axis or optical axis, okay? After reflecting from mirror, it passes through that point. So we say, okay, this mirror focuses that at that point, and we'll talk more about that. So the light rays are going something like that. So that's why the name converging as well. So converging mirror, concave mirror, same thing. Okay, two different name for same thing. One depending on its structure and how it's painted. Another one how it makes light to, let's say, behave. Converging based on the property of light, and concave based on its shape. Okay, so two different name. So when we put object in front of a mirror, we can see image. But for this kind of spherical or curved mirror, what happens? The distance of object and image often not equal. There is only one special situation when those are equal, but at all other places for the object, image distance is going to be different. Okay, so we are denoting them again by P and Q, and the relationship between image and object distance is given by this equation where this lowercase f, see there is this notation there, uppercase f is what we call focal point, but the lowercase f is the distance of that focal point from the mirror. Okay, so let's keep that in mind. So now we can use this equation, and if we know how far the object is, so that means if we know value of P, then we should be able to calculate value of Q, assuming that we know the focal length. Remember, focal length simply depends on geometry. And there is also easier way to figure out focal length. We'll talk about that a little later, maybe when we talk about lengths. Okay. So for now, these quantities, so you want to make sure that you remember and understand what P means here, what Q means here, and what F means here in this equation. And this equation has a reciprocals, just like we had, let's say, resistance in series or parallel. It was parallel, right? So it kind of looks kind of something like that, okay? And using geometry, we can prove this equation, but I'm not doing that here. So now, while using this equation, we need to keep in mind that some of these quantity could be sometimes positive and sometimes they could be, some of these could be positive or negative, okay? So here is detail, but in short, if something is real, then that is positive. So for example, if we have a real object, so for example, this object is standing there like a kid was standing there, right? So that is real. So distance, real distance, they are taken as a positive. But remember, we had a kid, the image of the kid was virtual. So when we have a virtual thing, then we take that as a negative, okay? Negative for virtual. And then we haven't talked much about, other kind of mirror, but we said, okay, we can polish on this side. When we do that, it becomes convex mirror or diverging mirror. So in that case, the focal length going to be negative for that. But for this converging or concave mirror, focal length is positive. So to use that formula, we need to remember how to use signs properly. If we don't, then our calculation or the result going to be wrong. Okay. Okay. So now here is my question for you. Okay. So image is here when object is there. Okay. So this is the mirror which is painted on this side. Okay. Polished on this side. So now, what do you think about sign of P, Q, and F in that order here, okay? Now I'm opening the poll, and you have a minute and 30 seconds to answer this question. So to use this equation, you need to master the sign. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So now let's see what we got. Oh, we have all of them kind of competing with each other, except D and E. Okay. So here, the real lines, the real ray of light, passing through this object here. Object is just standing in front of mirror, right? So the object is real. And image, on the other hand, see, the ray of light cannot reach there because they have to reflect from the mirror, right? So these are back produced rays of light. So that means is virtual. So that means Q is negative. P, on the other hand, is positive. And the mirror concave means focal length is positive. So that's how it works, folks. So that means P is positive, Q is negative, and F is positive. So positive, negative, positive, positive, negative, positive. So positive, negative, positive means C is the correct answer in this case. There was a little bit more for B. So it looks like some of you thought the object is also virtual. It is not. Okay, although we just draw a line to represent object, this is real object. See, real ray of light are passing through that. Okay. And how do you know real ray of light? See how I'm showing with the arrows. So when you draw these, make sure you draw arrow on them. Okay. So if you don't put arrows, uh, it does not correctly represent the ray of light. Now here is a question that we can use to practice using this, right? So it says an object is placed at a distance of that much, and that F is focal length. So rather than telling a number, it's given in terms of focal length. Okay, so object distance here is 0.5 F. So it's just standing in front of mirror. So object is placed, right? So you are putting it there. So that means it's a real object. It's not like somewhere behind the mirror, right? So that is that. And concave mirror. So that means F is, see, it's given in terms of focal length, but we need to make sure that we are using this as a positive. So when you are using this for concave, it's a positive. So even if you don't write positive, you're going to be using it as a positive, no problem. But when you use this for convex, then in that case, it's going to be problematic. So it's a good idea to practice like this. So that's that, and we are looking for Q. So our formula is 1 over P plus 1 over Q is equal to 1 over F, right? So we are solving for this, means we want to move this onto this side. So 1 over Q is 1 over F minus 1 over P. So this is given in terms of F, so I'm just leaving that as it is, and minus 1 over 0.5 F, okay? Or if we like, we can write this as half, like this, right? So see, this is in reciprocal. I think working with that's going to be a bit more practical. So 1 over Q is 1 over F, and 2 over F. So fraction of fraction, it inverts, right? So that means it's going to be 2 over 2F. Oh, both of them are F. Why am I doing that? Okay, so that means it looks like it's a 1 over F. So Q is negative F. So the image is forming at F. And this Q, so if the F was a number, let's say 10, and then this answer would be negative 10. So negative 10 means it's a virtual. So image is virtual in this case. That's what it is saying. Okay. So equal to the focal length, but image is virtual. Negative sign means virtual. Virtual at distance equal to the so that's how we use this formula, and that's what the negative sign means, right? So now I said, okay, focal point is F and distance is called lowercase f, right? So that's what I said. So now y is called f. I already said if we had a parallel ray coming out to this principal or optical axis, then they all, it does not mean they won't go something like that. They will, but all of them kind of meet at that point. So since they are meeting at that point, we say, okay, image is there. So here, these parallel means what? So parallel rays means, remember we talked about how sphere becomes a plane and the rays of light are parallel when we are far from the source. So that means the object here is far from the mirror. So all the lights that are arriving are parallel to each other. So when we say it's far or very far, numerically we may write that as an infinity. Okay, so object distance here, see, we cannot see where the object is in this sketch. So object distance is at infinity. Okay, and when object is at infinity, image is formed exactly at the focal point. And looks like this image is going to be very tiny because they are all meeting at that dot. So that's why the image distance here is equal to f, but this being real, it is not negative f. Okay, so it is slightly different from what we had, in that problem. In the problem, we got q as a negative f. So in that case, the image was forming somewhere there on the back. Okay, but in this case, image is forming in front, and this in front of mirror, right? And this point is the image point. So where is image forming? At the focal point. So what's the distance of focal point from the mirror? We call that focal length, and we denote that by lowercase f. Okay, so that's what we do. So looks like it's a good time to take a break. So let's take a break, and then once we come back, we'll talk more about how do we draw array diagrams to find the position of an object, right? So we learn how to use formula to figure that out, but we may be able to find in many cases, actually all cases, almost all cases, we can just draw 3 lines and figure out where the image is going to be if we are careful. Okay, so I'll see you. Welcome back. So when we put object at different distance from the mirror, what happens? It forms different kind of images. And I found this video, this YouTube channel named Learn and Have Fun, I guess, written slightly, shortened, I guess. So I captured this video from there, right? So if you are interested, please visit that and watch, right? But if you can see my screen, you can do that as well. So let's take a look. Here is a screen. So screen where the image is formed, okay? And in this corner, you see there is this mirror on a stand, okay? So now you can put object and see where the image forms, and you can move the object. So that's what this video is doing, okay? So let's watch. I think it does not have sound. Oh, there is music. So when object is far, in that case, this screen is put at a focal point of this mirror. And you can see there is tiny, tiny image, right? So there is this whole plane, and the image of that plane is tiny, tiny over here. So let's watch. So now you can see the plane, it's upright on this side. Over there, the tiny, tiny, it was kind of inverted. So the concave mirror is making inverted real image. And how do I know it's a real image? If you can show that on the screen, that means it's a real image, okay? So now what happens? This object is a little bit far from center of curvature or center of curvature of this mirror beyond C. So in that case, the image is formed in between F and C. F means focal point and C, right? So that's what we see here. And still the plane is kind of inverted. It's kind of hard to tell looking at this picture over here. It's upright, but of course you can tell that this is upright over there, but this is upside down or inverted. It's more clear when you have photograph in the light off. And the ray diagrams here, they are not drawn very correctly in some cases. So you can ignore the ray diagrams, just focus on the let's look at the image, how the image is formed. Really. Object and image, they are at same place. You can see the same distance from the mirror, and it's inverted. Now, if you notice, you are bringing, or the object is brought, is being brought closer and closer to the mirror. And image is being formed very farther and farther from the mirror. Oh, did not make. So that's how the image becomes virtual. See, you cannot catch that on the screen anymore. Okay. So you can see the image, but you cannot project that to the screen. So if you look at the mirror, you can see the image. It looks like it's inside the mirror. Okay. But actually it is behind the mirror. So that's how the image is formed. And here is one example where object is between focal point and the mirror. So the image becomes upright and it is magnified. Okay. So when you want to see details, that's how you want to position. You want to position yourself between the focal point and the mirror. Okay. So that way you can see the magnified image. Okay, so here is a ray tracing. So for this, we're going to be tracing 3 of them. Sometimes, yes, you can also draw 4 of them. Really required is just 2, but third one, helps us to make sure that we are drawing the other 2 correctly. So these rays are also called special rays or principal rays. Okay, I think I have written in my note principal rays. Here I also included this word special rays. So how do we draw that? So let's look one at a time. So you see we draw one ray, not in particular order, but let's look at the red colored one. So that is coming parallel to the axis, and we already know any ray coming parallel to the axis reflects, and after reflection, it passes through the focal point of the mirror. Okay, so that is one. So how to draw it? So you draw a mirror, you put object in front of mirror, so you draw something like this. And then after that, what do? You starting from tip of that object, you draw a line parallel to this principal axis here. So this line is drawn that passes through the center of the mirror. Okay. So there is this C. This is also center, but this is center of curvature, we call. It is center of a sphere from where this mirror come from. The C is, but the center of mirror is this point that I am pointing here in this image, in this diagram. and the principal axis goes something like that. So it crosses perpendicular to that point over there on the mirror. Okay, so that is one line. Now let's look a green line. Okay, so this green line is headed. So you start from the tip and then you draw straight. Remember, in one medium, it just keeps traveling in a straight line. So until it hits the mirror, it is just moving in the air. So that means it's just going to go straight. Okay. And then after reflection, what happens? It follows the law of reflection. Of course, all of these follow the law of reflection, but in this case, this principal ray or the optical axis, sorry, principal axis or the optical axis acts like a uh, normal to the mirror. So that's why this angle here and that angle here, they are equal. So we can say, okay, this is incident angle and this is reflected angle. So that's how we know which way to draw. So here there is the center of mirror, tip of the object, you know. So you connect that line using a ruler, right? And then once it is there, how do you draw this? By making this angle, by making this angle here equal to that one. So you put a point where the angle is equal. So if you have protractor, so you can use that and draw it, okay? And then that's the second line. So now what you see is this red line and this green line, they are meeting at this point. So that's where the tip of the object appears. So that means the image, top of the image is down here. And this is formed over here. So we can say, okay, we can draw a line representing the image. And this image, to verify that we drew these to correct, we can draw another line that looks like like a opposite of this one here. See, if you pay attention, red line and green line, sorry, not green, but the blue line. So you can see it was coming parallel, and after hitting the mirror, what happened? It went through the focus. Now, what is this doing is kind of reverse. Let's say if this red light was to reverse, went from the focus, and then from that it goes parallel, right? So something like that's happening for the blue line here. It passes through the focal point here and then hits the mirror. And after it hits the mirror, it gets reflected parallel to this line here, principal axis or optical axis. So that's how we draw it. So when we draw it carefully by measuring, and that's what I did when I was drawing this, okay? And so in that case, what happens? All of these three meets at that point. And of course, after that, they can continue. That's fine. But wherever they are meeting, that's the point where the image gonna be. So this image is real. And by the way, that's for the blue. So this is real, inverted, and smaller in size compared to the object. So when we compare the size of image and object, we call that magnification, right? So magnification in this case is going to be less than 1, okay? When image size and object size, they are equal, then magnification is 1. And when image is smaller than the object, magnification is less than 1. When image is larger than object, that's when magnification is, we say, okay, the image is magnified, okay? So that's how it works. And there is formula for magnification. Looks like I did not write so far in the slides. So magnification, we usually denote that by M, sometimes uppercase, sometimes lowercase, but I prefer lowercase for that. And that is equal to size of the, oh, there is negative sign here, and height of the object divided by height of the image. Oh, did I go other way around? Yeah, looks like I went other way around. Okay. height of the image divided by height of the object. Or we can just write that in terms of distance of the image and distance of the object. So negative image distance divided by object distance. So why negative sign? See here, this is inverted here. So to represent that, so in this case, Q is positive, P is positive. So that means magnification is negative. So to represent inverted image, we put that negative sign. So the negative sign is there in the definition of magnification. Okay. Okay, too much talking from me. So now it's your time. So go ahead, choose a correct answer. Oh, A, B, C, D are right there, right? So A is here. So this is the, oops, this is the original ray, and these are the possibles. So which one you think is the one that represents the reflected ray? Okay. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. Oh, it did not stop. Oops. So there is a bit more for D, and that is correct answer. Remember, this ray of light is coming parallel to this optical axis or principal axis. So when it hits the mirror, it reflects and passes through the focal point. So that would be focal point here. So the ray of light gets reflected from light, so it cannot go behind. So this cannot be correct. Okay. And so now over here, it's not going that way because the mirror is carved this way. So it brings it down there. So that's why A is not correct answer. Okay. C is not even coming out from the point it's hitting. Okay. So that's why C cannot be correct. So reflected ray has to be drawn from the point where the incident ray is hitting. Okay. So that's how we need to draw. So if we are drawing something like that, we're not doing it right. Okay. So now there is another question without picture. Let's see if we can figure that out. Let's do 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got. Mostly A and then B and D competing, right? So let's see what it is saying. Can we try to sketch this? A ray of light originating from, so I guess I want to draw like that, and tip of an object. So tip of object, draw like that, okay? object passes through a focal point. So focal point is somewhere there, right? Or could be somewhere here. It could be anywhere. So let's say it is here. Okay. So that means it goes from focal point means it's arriving here. Okay. So that's what's happening. So when it does, it comes parallel to the axis. Okay. So the ray travels parallel to the principal axis. So I think that's what we had here mostly. Okay. So that's what happens. So ray wouldn't be returning through the same path here. Okay. So there is one ray that's going to return to the same path. So if this is F, I think C going to be here, center, okay? So if you draw something from the center, so that becomes a radius. So radius is perpendicular to the mirror. So that is the only ray that gets reflected, okay? So other than that, maybe I should be drawing, if I want to draw that, it should be going through the tip because we draw all rays just going through the tip, right? Maybe something like this. So that one that starts or passes through the center of curvature, not center of the mirror, but center of curvature, that's going to trace back. But we're not talking about that, okay? So that's why this is A is correct answer in this case. So now this is a bit long. Let's see if we can comprehend this, okay? So for this, let's say 1 minute and 30 seconds. So if you recall this, then that's how you draw the ray diagrams. Thirty more seconds. Five more seconds. Five, four, three, two, one, and it stops. Let's see what we got. So mostly B, and that is correct answer. So if you can keep this in your head, you can draw after practice. And you can also tell if certain drawing is correct or not. Okay. So hopefully you have this in your head. So now you see here, object here is in between focus and the center of the mirror. Okay. So it could be anywhere. Okay. It could be anywhere in this line from starting from here to here or there. Okay. The ray diagram we draw are going to be exactly same. Okay. The way we draw or the nature of the image is going to be exactly same. So when does the image becomes virtual? See, this is virtual image. So when does image becomes virtual? When object is in between mirror and the focal point. Okay, somewhere here, anywhere these points. Focal point is a special case. Still, it's gonna be kind of, you know. So yeah, even the focal point is not gonna converge. So I think I have another diagram. Okay. So in between these 2 points, everywhere, no matter where you put, this gonna make virtual and upright. See here it's magnified. And if we were to calculate magnification for this, it's going to be positive. Why? Because the image distance here, oops, image distance Q is negative. So when you put negative in that formula that has negative, the result becomes positive, right? So anyway, so the first we talk about the light that goes parallel, so that goes through the focus, so that's why it is doing like the way it is drawn, okay? And the one that heads to the center of the mirror, follows the law of reflection, assuming this as a normal, okay? So these angles are equal, so that's how I draw it. And then in this case, from the focus, see the focus is behind the object, so you want to start uh, to draw the line from the focus and must pass through the tip, okay? And then that's how you draw this portion of the line. And after, since it is coming from the focal point, we know it goes parallel. So if we look at this line, that line, they're not going to meet on this side. To form an image, these rays of light has to meet somewhere, but they are not meeting. So that on this side, so that's why it's not forming a real image. But if you look at the mirror, you see there is image, looks like it's inside the mirror. So to figure out that, what we do is we back produce this reflected light. See, this one is reflected, this one is reflected, this one is reflected. So we are back producing them. So when we do that, it meets at that point. So that means that's where the image is. So that's how we look at it. Okay. So we already saw what happens when an object is beyond focal point. Now we saw what happens when an object is within a focal point. And now let's look at a situation where object is exactly at the focus, okay? So at that point, see, I drew the one line that goes parallel and then passes through the focus, right? Another one goes to the center and reflects like that, but I cannot draw a third line here. So see, the third line has to start from the F or from the tip and go like that, right? So third line, so it's not going to the mirror. It's not going towards the mirror, so that means that line does not make much sense here. So I'm just leaving it. So now these becomes parallel. Okay, so these rays of light becomes parallel. So parallel line theoretically never meet. So they don't meet. So if we back produce, so these are parallel, so these are also going to be parallel line. But so that means there shouldn't be any image, okay? But what happens is that is a very theoretical case when it is exactly at focus. In practically, it might be slightly off. So when that happens, what happens is you can see the image behind. So that's why we say, okay, image is at infinity. Okay. And on the video, if you paid attention, it was showing that image. Okay. So on practice, what we do is we bring this little bit closer, and then you have, at very large distance, you have a magnified image, and that's what you see, highly magnified image. Okay, so all together, the pictures I showed you, the ray of light coming from the very distant object, right? And one that is with far from the object, far, but it is not at infinity, so it is behind the C, So you see this image forming something like that. We saw that. So image becomes a smaller size. We call that reduced. In this case, it was tiny, right? And now for this one, these two, those are magnified, and this one highly magnified, and this one is just magnified. So that's how it looks. So this mirror can make smaller or larger object. So to make the, sorry, I should say image, it cannot make object, right? So to see the magnified image, the object has to be within the focus, okay? So that's why if you are using the mirror, so you cannot be very far from the mirror, okay? If you are very far from the mirror, what happens? You can see the image, but it's not going to be magnified image, rather it's going to be smaller. But one advantage is that the field of view becomes larger. So for the distance object, what happens? The images are tiny, so it can fit the larger area on the mirror. So here is this picture where you see there is a plane mirror and it covers this much field of view. But if you use, oh, it is turns out to be a convex mirror here. Ah, looks like I messed it up. So convex mirror or concave mirror, when object is, within the focus, that basically produces large field of view. So speaking of convex mirror, what is convex mirror? So it is also part of spherical mirror, just like this. But this time, this section you cut, now you are painting on this side, making this side shiny, okay? This side is shiny. So before we had this shiny, inner side shiny, but now outer side or exterior shiny. So this is my polish that I'm using to make it shiny surface, okay? But the center of the sphere is still on this side here, okay? Uh, so that means focal length is on this side, the back side of the mirror. So that's why we say, okay, focal length is negative for convex or diverging mirror. Okay. So object is in front of mirror. Of course, the object has to be in front of mirror. Okay. So this distance is p, just like that. And then now let's say image forms behind. So that means it is a virtual image. So always, this one always makes virtual image, okay? Unlike concave mirror, the convex mirror always makes virtual image. So how do we draw a ray diagram for this? So here is one example. And no matter where the object is, this is gonna look just like this, okay? So the image always gonna be in between this and the focal point. And so process of drawing, let's see if I wrote those, okay? Parallel to the axis, just like this. But now, this time, it's not coming back towards focus. It's a diverging mirror. See how it is carved? So it goes like that. So now, how do I know it's going to go exactly like this? So for that, look at here. The focus is there, right? So when you look, it looks like as if it was coming from the focal point. Okay, so that's how you need to draw. So back produced one reaches to the focal point. So parallel to the axis reflect as if it's coming from the focal point. So slightly different there, but still three rays of light we choose, principal rays. And the green, exactly same, it hits the center and gets reflected, okay? Uh, Following the law of reflection there with the normal being the optical axis. So green is that. Now, how about blue? Remember, blue we used to, the one we drew blue from tip of the object to the focal point of the mirror, okay? So that's what we did for the concave. Now for the convex, what do we do? Okay, focal focus is not on the side, so we're gonna draw as if we were heading to there. But since there is this mirror, the light cannot cross the mirror, so it gets reflected. Okay, it gets reflected following the law of reflection. Uh, and in that case, this becomes now parallel to this, just like we had for the concave, case of concave. So this becomes parallel to this one here. So that's how I know where to draw this, okay, without measuring angle here. So when I back produce, it's gonna go there and gonna meet with this dashed line. So that means I know the image is gonna be there. And to make sure, we have third one as well. You can count this as a third or this one as a third. Okay. So if you have just drawing two, I think it's mostly depending on situation, you may draw this one and that one, or this one and that one. But if three can be drawn, then you want to draw all three like this. So the image is always going to be virtual. So that means image distance is negative. So magnification is positive, means image always going to be upright. Okay. Upright means in the same direction as the object. Okay, orientation of image is going to be same as the orientation of object. If object was down, then image would be pointing down as well. So although it's down here in the drawing, we call this upright because it is in the same direction to the object. Image is pointing same direction to the object. Okay? So that's what we do. That's how we draw these three principal rays or special rays for the convex mirror. So now here is a question for you. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. Oh, we got all of them. So this is diverging mirror, which means also convex mirror, diverging or convex. Okay. So this ray is the principal ray that's coming parallel, right? So what happens? It's gonna, reflect. Oh, looks like, what did I do here? So this is shiny surface. So that means it would be reflecting something like that. I think I messed it up. Okay, so that's why you have these varieties of answer. Okay, so as if it was coming from this side there, right? So it cannot converge, so it cannot be E. And these are polished, means it cannot pass through that. Yeah, this one I made mistake here. I did not put the correct answer here. Okay, my bad. Sorry about that, folks. So moving on, let's look at this question. So we use the same formula for the concave and convex mirror, and we talk about lens next class. We've used the same formula. Okay, formula is same. So object is placed 18 centimeter in front of convex mirror. So object is real. So Q, not Q, but P. P is 18 centimeter. So there is another also in centimeters. So we can work on centimeters here. We don't need to convert, but if you like, you can. And focal length here is 12 centimeter. But since this is convex mirror, focal length of convex mirror is negative. Okay. So now it says determine the location of image using mirror formula. So Q is what? So in this case, I'm leaving you this as a homework for you to draw the ray diagram for this, okay? So let's use formula quickly. So 1 over Q plus 1 over P is 1 over F. So these are being added, so we can write in any order. 1 over Q is 1 over F minus 1 over P. So now, how do I do it? 1 over Q is P minus F over FP. I'm using a little bit, algebra over there or arithmetic. So Q gonna be FP, P minus F. So if it is too much for you, you can just do this in calculator and invert it to get Q. So make sure you invert to get Q. So now we can put these numbers here. So one is 18, another one is 12, but we know 12 is negative, so that means it's going to give us negative. And then divide that by difference of this. So P is 18 and F is 12, so that means it's going to be positive 6. Okay. So now 6 times 2 is 12. Oh, I don't know if I got this right. So image for this convex mirror should be negative. We are getting negative, but it should be less than F. So what mistake I am making here? Looks like I am getting 36, but it should be less than 18. What did I do? So let's see, P minus F and then FP. So FP, P minus F looks like, correct, but something is not working well. So maybe you want to plug in numbers right here and see if we get the same number in with the calculator crunching. This algebra should be correct. I don't know why. So 1 over F is, did I do F and P kind of? No. So F is 12, 1 over 12, and this should be negative. And then this one, oh, I see what happened here. P and F, so they get added, not subtracted. Okay, 12 and 18 is positive. How much? 30? Yeah. So now that makes sense. Okay. Yeah. I forgot that negative sign for the F. So anyway, folks, so that's how we get the answer. I think we get around what, 7? Negative number, and I think we get 7 or something like that. So I'm not very good at doing multiplication and division at once for something like that. Okay. So this is how we calculate. Rest is algebra and arithmetic. And I think this is now correct. So I'll just leave it here, folks. So I'll see you next class. Fast before spring break. Hey!